In 2025, Apple quietly shelved the second generation of its mixed reality headset after internal testing revealed that users abandoned the device within 11 days of purchase. Not because the technology was broken, because wearing a computer on your face still felt ridiculous. But here's what Apple did not tell anyone. Buried inside that same report was a separate project, codenamed N401, describing a form factor so thin it passed for regular eyewear and blind user tests. Participants wore it for 6 hours straight without noticing. The engineers who ran those tests described it as the moment the hardware problem was effectively solved. That project is now the fastest-moving program inside Apple's most secretive division. And Apple is not alone. The race to replace the smartphone is not 5 years away. The infrastructure to do it is being assembled right now. To understand why this matters, you need to understand what is actually at stake, and the numbers are startling. The global smartphone market is worth approximately $500 billion annually. Every major technology company on Earth has built its revenue model on top of that device. Google's search dominance, Meta's social advertising, Samsung's hardware empire. All of it depends on the assumption that your primary computing surface is a flat glass rectangle you carry in your pocket. The moment that assumption breaks, the financial architecture of the entire technology industry reorganizes overnight. But the stakes go well beyond corporate profits. There are currently 6.8 billion smartphone users on the planet. Each one interacts with information the same way. They stop what they are doing, pull out a device, look down, and re-engage with the world after. That friction is so normalized that we have stopped noticing it. Researchers at the University of California, Irvine, published findings showing that after a single smartphone interruption, the average person takes 23 minutes to fully regain cognitive focus. Multiply that by the average 96 checks per day that smartphone users perform, and you begin to understand that the smartphone is not just a communication tool. It is a cognitive tax that billions of people pay every single day without realizing it. The second major stake is geopolitical. Whoever controls the dominant AR platform controls the interface layer between human attention and reality itself. That is not a metaphor. It is a literal description of what augmented reality does. China's government has already designated spatial computing as a strategic national priority, with $14 billion in state-directed investment flowing into companies like XREL, Rocket, and TCL's Thunderbird division since 2023. The United States, through both DARPA contracts and private capital, has funneled comparable resources into companies like Magic Leap, Brilliant Labs, and Meta's Reality Labs division. This is not a consumer electronics race. It is a contest for the next platform that mediates how humans access information about their world. The story of how we got here starts further back than most people realize, and the early path was genuinely humbling. In 1968, Ivan Sutherland built the first head-mounted display at Harvard. It was so heavy it had to be suspended from the ceiling by a mechanical arm. Sutherland called it the Sword of Damocles, which was both poetic and accurate, because it literally hung above the user's head. For the next 4 decades, the basic problem remained unchanged. The optics required to project a stable, bright, full-color image into the human eye at close range demanded components so bulky and power-hungry that miniaturization seemed physically impossible. Google Glass arrived in 2013 and showed the world what was possible and what was not. The technology worked. The social experience did not. Wearing glass in public made people uncomfortable, partly because of appearance and partly because of the camera. The product was discontinued for consumers in 2015. But this is the part most people got wrong about glass. It failed as a product, not as a proof of concept. Microsoft's HoloLens, released in 2016, demonstrated that spatial anchoring, the ability to fix a digital object to a specific point in physical space, was achievable at consumer scale. Magic Leap raised $2.3 billion between 2010 and 2019 trying to push further. The hardware kept outrunning the optics. Think of the problem like trying to project a cinema-quality film onto a soap bubble without the bubble popping. Every component had to be smaller, lighter, and more energy efficient than anything previously manufactured, all at the same time. What changed is a convergence of 3 engineering breakthroughs happening simultaneously, and the first one is the least understood by the general public. It is called Waveguide optics, and it is the reason AR glasses can now be thin enough to pass as normal eyewear. Here is what most people do not know. The Waveguide displays being manufactured today by companies like Lumos and DigiLens are capable of projecting images at a resolution of 60 pixels per degree across a 50-degree field of view. That is the threshold at which the human visual system stops detecting pixelation. The image appears to float in real space. What makes this remarkable is the physical mechanism. The waveguide is a piece of glass approximately 2 millimeters thick. Light enters from a tiny projector embedded in the temple of the glasses, bounces through the glass using total internal reflection, the same principle that makes optical fiber work, and exits toward your eye across the entire lens surface simultaneously. The reason this matters beyond the obvious is what it implies about power consumption. Previous AR systems required high-powered projectors because light was being aimed at a screen in front of you. Waveguide optics redirect existing light with almost no energy loss. The display component of current waveguide AR glasses consumes approximately 80 milliwatts of power, compared to the 800 milliwatts consumed by an equivalent smartphone screen. That is a tenfold reduction. And because the display is the single largest power draw in any wearable device, this breakthrough effectively solved the battery life problem that killed every previous AR attempt. A device drawing 80 milliwatts from a small battery integrated into the temple or frame can run for 12 to 14 hours. That is a full waking day. The implications of that single number are enormous, because battery life was always the hard ceiling on AR viability. Now here is the part that overturns almost everything the tech press has told you about this transition. The common assumption is that AR glasses will replace smartphones by becoming better smartphones, better screens, better speakers, hands-free access to the same apps. That framing is completely wrong, and it is wrong in a way that actually makes the replacement happen faster, not slower. The smartphone replaced the camera, the calendar, the map, the newspaper, and the MP3 player not by being better at each of those things individually. It replaced them by eliminating the concept of the separate device entirely. AR glasses are not doing the same thing to the smartphone that the smartphone did to the camera. They are doing something more fundamental. They are eliminating the concept of the screen. When your display is the world around you, the question of screen size becomes meaningless. You can have a 200-inch virtual monitor floating in front of you while sitting on a train, and no one next to you sees anything. Meta's internal research, published in early 2025, showed that users given access to persistent virtual screens in AR environments voluntarily spent 340% more time on productivity tasks compared to equivalent smartphone usage. That number did not come from the device being more capable. It came from the device being less interruptive. The information came to the user's field of vision contextually, rather than demanding that the user redirect their entire attention to a separate object. And here is what that 340% figure means in practical terms. If your productivity on a device scales by that factor, the economic case for employers to equip workers with AR devices instead of laptops and phones is not a question of preference. It becomes a question of competitive survival. The mechanism that makes all of this cohere is edge AI processing, and it works in a way that most people find counterintuitive. Your first instinct is that a computer this small cannot run the sophisticated image recognition, language processing, and spatial mapping required to make AR useful. That instinct was correct in 2020. It is no longer correct. The Snapdragon AR2 Gen 1 chip, which began volume manufacturing in 2024, is designed specifically for split processing AR workloads. Here is how it works in practice. Your AR glasses contain 3 distinct processors. The first is a dedicated spatial processor that runs at extremely low power and does one thing only. It maps the geometry of the room around you 60 times per second, building a real-time, 3-dimensional model of your environment. The second is a vision processor, roughly equivalent in capability to a 2021-era smartphone chip, which handles object recognition and text processing. The third is a communication chip that sends complex tasks, things like generating a response to a voice query or rendering a photorealistic virtual object, to a nearby device or cloud server in under 8 milliseconds. 8 milliseconds is below the threshold of human perception for latency. The handoff is invisible to you. Think of it like a relay race where the baton passes so fast you cannot see the exchange. The result is that you experience a device that appears to have the full processing power of a server farm, running from a package that weighs 45 grams and sits on your face. The complications are real, and the most honest account of this technology requires confronting them directly. The most serious is privacy, and it is not the privacy concern you have probably heard about. The fear most people express is about cameras recording in public. That is a legitimate concern. But the deeper problem is environmental data harvesting. AR glasses, to function properly, must continuously build a spatial map of every space you enter. Every room, every office, every home you visit gets mapped and stored. Meta's privacy policy for Ray-Ban smart glasses, updated in 2025, explicitly reserves the right to use spatial data for advertising inference. That means the physical geometry of your home becomes an input into the advertising algorithm. There is no regulatory framework anywhere in the world that currently governs spatial data with anything close to the rigor applied to financial or medical data. The second complication is the display brightness problem in outdoor sunlight. Current waveguide displays operate at a maximum of approximately 10,000 nits of brightness. Direct sunlight measures around 100,000 nits. The result is that in bright outdoor conditions, AR overlays become nearly invisible against the sky. Companies are addressing this with electrochromic lens dimming, which selectively darkens the surrounding environment to increase contrast. But electrochromic dimming introduces its own hazard, artificially darkening a user's vision while they are operating in a physical environment creates documented depth perception errors. The FDA opened an initial inquiry into this specific risk in late 2025. For you personally, the transition has a specific timeline that affects concrete decisions. If you work in any field that involves information retrieval, design, navigation, or communication, which is most knowledge work, your employer will begin piloting AR devices as productivity tools between 2027 and 2029. By 2030, the major smartphone manufacturers have already publicly committed to releasing dedicated AR form factors. Samsung's Project Muhan roadmap targets 2028, and Apple's internal documents leaked to the information in March 2026 describe 2029 as the target ship date for a consumer-grade AR glasses product under 40 grams. What this means for you practically is that the software skills you build on flat-screen interfaces, your muscle memory for apps, navigation gestures, and organizational systems, will need a significant rebuild. The interaction model for AR is fundamentally spatial rather than sequential. You navigate by looking and gesturing, not by scrolling. Companies like Figma and Adobe have already begun training their design teams in spatial interface principles, which tells you something important about where the job market for digital skills is heading. If you have children under 10 today, they will likely never carry a smartphone as their primary device. That is not a prediction designed to sound dramatic. It is the conclusion you reach when you map the engineering milestones already achieved against the timelines publicly committed to by the largest hardware companies on Earth. Here is where this ends up, and the perspective is worth sitting with for a moment. Every dominant computing platform in history has lasted roughly 15 to 20 years before being displaced by something that eliminated a fundamental friction. The desktop eliminated the need to visit a physical terminal. The laptop eliminated the need to be in a fixed location. The smartphone eliminated the need to be near a desk. AR glasses eliminate the last remaining friction, the need to stop engaging with the physical world in order to access digital information. When that friction disappears, the boundary between the digital and physical environments does not blur. It dissolves. What comes after that is not a better phone. It is a different relationship between human cognition and the information layer that increasingly